Okay, so it is truly an honor and a privilege to be here today to chair the Grace Wahba Achievement Award and Lecture. And for those who don't know, this is a pretty new award that was started in 2021 to honor Grace Wahba. Grace is an American statistician and an emeritus professor of statistics at University of Wisconsin-Madison. Many of you know Grace, and she really requires no further description. But for those who don't, she's a statistician who's made fundamental contributions to mathematical and applied statistics, optimization, and machine learning over the course of her very long career. She laid the foundations for smoothing noisy data and is regarded as the mother of smoothing splines. And her work has integrated advanced mathematics such as reproducing kernel Hilbert spaces, generalized cross-validation, and powerful computation methods based on the representer theorem into a broad class of regularization approaches. These approaches, which are now standard in the field, have profoundly impacted practical applications in science, engineering, and medicine. She really is just such an accomplished statistician and a really wonderful person for the people who've had the privilege of getting to know her. So this is the Grace Wahba Lecture, and of course today we're here to celebrate the accomplishments of this year's Grace Wahba Achievement Award recipient, who is none other than Nancy Reid from the University of Toronto. So Nancy sent me by email an extremely short bio that was completely inadequate for this occasion. It was much too modest. So I'm going to elaborate here, and Nancy, if I have any of this content wrong, then it's because I used Wikipedia, and if the delivery falls short, then it's because I didn't think to use ChatGPT. So Nancy got her bachelor's, master's, and PhD degrees from Waterloo, UBC, and Stanford. She started her faculty career at UBC, University of British Columbia, and then spent most of her career at Toronto, where she's been the first woman to hold the Canada Research Chair in Statistics. I cannot even list the awards she's won because it would take the whole lecture, but just to name a few. She won the Guy Medal in silver from the Royal Statistical Society. That wasn't enough, so she went on to win the Guy Medal in gold. She won the David Cox Foundation of Statistics Award. She's been a COPS Distinguished Achievement Award and lecturer. She's a fellow of the Royal Statistical Society of London. She's won the FN David Award from COPS. And she's an elected fellow of the IMS, the ASA, the ISI, AAAS, the Royal Society of Canada, just to name a few. Nancy has also performed tremendous service for our field that has just been invaluable. She's the current president of the Bernoulli Society, but has had many other contributions over the years, including as former president of the IMS and the Statistical Society of Canada, and she more recently has been co-editor of the Annual Review of Statistics and its Applications. And of course, we're here to honor Nancy for her research first and foremost, which has centered on foundations and properties of methods of statistical inference, focused on discovering how inferential statements can accurately and effectively summarize complex data sets. So with no further ado, our lecturer, Nancy Reid. Oh, I'm so sorry, I'm going the wrong way.
Thank you. Thank you very much, Daniela. And thank you to the IMS. It's, of course, a great honor to win this medal in Grace's name. I started by asking Doug Nitschke which of Grace's papers I should read in preparation for this lecture, and they were all a bit too hard for me. So I went to Google and looked up some pictures. And what struck me about this image cluster from Google is how happy Grace looks, how much fun she seems to be having. And I think everyone who's had a chance to work with her will echo that. The famous Thursday group at Wisconsin and so on. It's just, she's brought a lot of joy to statistics as well as a lot of talent. I did spend quite a bit of time on this article, and I would encourage people who haven't read it to have a look. And I looked again yesterday and realized that I just missed a chance to wish her a happy 90th birthday, which was 3 days ago. So Grace is a little bit older than me. I'm not 90 yet, but I hope to get there. And younger than Betty Scott and F.N. David and so on. But there's a kind of unspoken camaraderie, I think, among women in statistics who don't talk about it that much. But we all kind of realize that we are where we are because of the people that the women who went before us. Every little step makes it a bit easier for the next step. We're in a pretty good place today. And you can tell by this meeting, right? Just look around. There's lots of people of all diverse types, and that's one of the strengths of our field. But it wasn't always this way. Your hair will curl when you read the interview of Grace's early days. We're here because of people like Grace. And perhaps younger people are here because of people like me. Each little nudge makes it a little bit easier, and for that I'm quite grateful. And I don't often speak about it, but it seemed like the right occasion to mention it. Today I said I would talk about models and misspecification, and I will. Most of the talk is based on recent work with Heather Batty, but I'm going to start from a more general place, and one thing that I've got in the habit of doing is just haphazardly selecting some examples from the scientific literature and kind of having a quick scan to see what kind of stats they used and was it any good and would I have done it differently. So I'm going to start with these examples, and this is really quite haphazard. They're things that came across my desk basically this summer, and usually from Twitter, but sometimes from more respectable news outlets. This article was, I think I did get this from Twitter, but I'm not quite sure. It was an article claiming that you could use data on wine quality as a kind of climate proxy, especially during the Middle Ages, let's call it, because they kept better records of the wine than they did of the weather, is the short of it. And so this paper purported to do that. I'm going to give like a super high-level, almost trivial overview of a series of papers, so I can't answer any questions about wine quality and weather really, but I just wanted to mention it because the scientific question leads to a data collection, as we know, and then to a statistical question. The scientific question is, can historical records of wine quality be used as temperature proxies? This is observational data, obviously, and they were a little vague about their statistical model, but it was basically a linear regression. Although this is a time series, it was really, it was an autoregressive regression. They used some information on temperature and precipitation, related that to wine quality, and then tried to see if the model was helpful for the years when there wasn't much data. And their conclusion was a sort of tentative, yes, they might be able to be added to other indirect measures of climate, but you need to be very careful about the source. This one I definitely saw on Twitter. This is one of several articles that have come out recently about guaranteed basic income. But this is a particularly interesting one because it's a randomized controlled trial of a guaranteed basic income. Not really a guaranteed basic income, an income supplement. And people were randomized to receive either $1,000 a month or $50 a month, and the groups were compared. And what you can sort of see from the picture, you won't be able to read the fine print, but at the very top there's a line to the left, and that's working, so people worked fewer minutes in every day, once the people who had the income supplement. But the more interesting sociological question is whether that inspires people to do other things, more entrepreneurial things, maybe invest in upskilling, for example, or opening their own shop or whatever, so that in the long run, although there's a labor market decline in hours worked, for example, in the long run, that's a labor market benefit. At the very bottom are leisure and other activities. So it seems that at least with this particular group, that time that they didn't spend working was not spent upskilling, but it was spent in leisure activities. So that's, as I mentioned, the scientific question: does guaranteed income supplement affect labor market measures? And the statistical model, again, was a linear regression with a kind of very, very high dimensional covariates, which were selected using the lasso and so on, but pretty familiar model for us. And the conclusion was that there's sort of support for both sides of the debate. So one side of the debate is don't give people money because they won't use it productively and they'll work less, and the other side of the debate is yes, but they'll use it in ways that are meaningful to them. And so in that sense, it's a net benefit. And these economists came down kind of on both sides of that debate carefully, like statisticians, right, very cautiously said, yeah, but you can see both sides. This example is from the University of Toronto, and it's this was made the news in Canada, I guess, because it's from Toronto. And this is about breast cancer mortality, comparing bilateral mastectomy to unilateral mastectomy in women who have cancer only in one breast. So many women will elect to have a double mastectomy to prevent a recurrence. And it is effective for preventing recurrence, but at least according to this data, it doesn't seem to be effective for prolonging survival. This was a matched case cohort study, the details of which are pretty tricky, and I wouldn't want to say this was the last word in the study because I thought the details needed a lot more study than I'd given them. But as you can see from the picture, they used the Kaplan-Meier method to estimate survival, and their conclusion was that the preemptive surgery did not appear to reduce the risk of death. I was kind of, I don't know why I have two on mortality. I do know why I have two on mortality. It's a little bit depressing, I'm sorry, but I chose this one because it's a twin study. So these are discordant twins. One has dementia and one doesn't. And so they were able to compare the survival. And it's kind of like a found experiment or a natural experiment, right? It's not a randomized trial, obviously, but because they're twins, they can assess somewhat the effect of, additional effect of dementia on mortality, other than the effect that operates through maybe having weaker heart or different genetic predisposition and so on. And this was a somewhat more sophisticated model, you would say a multi-level Cox regression with random effects. Their conclusion was that there is some genetic variation that contributes to the association between dementia risk and mortality. Kaplan-Meier curves, but these are after doing a multi-level Cox regression. And I chose this because I'm going to talk about matched pairs when I get to the more technical part of the talk, and this was an example of a matched pair study. And finally, this is completely different and not depressing at all. This is a work in astronomy on the variability of X-ray jets that have been measured by the Chandra telescope. And I know about this work because the authors, Meyer et al., it's a long list of authors, but one of them is Yanbo Tang, who was my PhD student, and he worked as the consulting statistician on this. And so that was kind of a fun project for us to discuss. And it's observational data, of course, but roughly speaking, I apologize to the astronomers in the room, are observations of X-ray jets consistent with current theory of their production. And the statistical model was relatively complicated in some ways and simple in others. It was to compare the background and the source measurements using the Poisson distribution. So these are the background measurements, have a certain standard rate, and then these AIs are known numbers that account for the time window of observation. And then the potential sources have also the same background rate with a known window for observation, plus some possibly upscaled rate. And the hypothesis of interest was to test if all those mu's are zero, in which case there's no extra variability. And the conclusion was that there was some extra variability and not compatible with the current thinking of the proposed mechanism for creating this. If that sounds vague, it's not because it's vague in the paper, it's because it's vague in my head. I don't exactly know what that means, but the astronomers were quite excited because it seems to cast doubt on a particular theory for how these X-ray jets are formed. Okay, so really what I wanted to do was show a bunch of different models so that I could talk a little bit about models and why did they use those models. And well, sometimes it's because that's what people use in that field. I think maybe the income supplement example was a little bit of that. We use autoregressive time series, and we had a treatment effect, and we had a randomized controlled trial, but we controlled for covariates anyway because we measured a gazillion of them, so we should use them. Maybe it's just standard in the publications of that particular lab. You know, these people collect very elaborate data sets and then often will publish a whole series of papers investigating different questions. The data is very expensive to collect, and it makes perfect sense to use the data for many different questions. And so they tend to develop a kind of strategy for analysis that they use repeatedly. That is the case with the breast cancer data. It's based on a huge population registry. Maybe more often, there's a kind of prescription or a feeling that this is what the statisticians would tell us to do. If there's a binary response, we should use logistic regression. If it's a time to event, we should use the proportional hazards model. If it's a time series, we should use a time series model, and so on. And we have these various different kind of look at the structure of the data and pick the simplest model that you can work with for that data structure. And very occasionally it's motivated by theory, like the X-ray jets and the Poisson distribution motivated by physical theory, but that tends to be somewhat less common for the types of data that we see, perhaps. Well, I suppose it depends what we work on, but for observational data, it's maybe a bit less common. There's, so we don't talk about these, at least I feel we don't talk about this type of model selection. This is not model selection in the way like I have a model or have 5 models, which one is the best. It's like, where do we start? And we tend not to teach it very much, and we tend, I feel, not to discuss it terribly much. But there are some pretty valuable sources that I find quite valuable. One is Davison's book on statistical models. I like this second bullet point quote: the art of modeling lies in finding a balance that enables the questions at hand to be answered or new ones posed. More familiar to ourselves and our students is that variability via probability is kind of key to statistical models. Cox and Donnelly has a lot written about modeling with using probability models as an aid to interpretation. Somewhat similar to what Davison said, I guess. A nice distinction between 2 types of error that is made in Cox and Donnelly's book that we don't often make. Perturbations of no intrinsic interest that kind of mess up the data, and natural variability that's really important to understand and is important to the phenomenon. Roughly speaking, you might say physical sciences is faced with perturbations of no intrinsic interest, and the observational data in the social and medical sciences has so much natural variability that we really need to find clever ways to accommodate it. There are 2 Fisher lectures that were written up in the same issue of Statistical Science by the giants, Lehman and Cox. And that talked about empirical or predictive models and contrasted with explanatory models. This is 1990, and now we're in 2024, and of course, there's been lots and lots of discussion, not just in 2024, the last 20 years, I guess, but not maybe the last 34, on the difference between predictive models and explanatory models. And statisticians get a little bit smug and say, yeah, but our models help you understand what's really going on, and machine learning people get a little bit smug and say, yeah, but our models do stuff, which is more important than that. And And actually, in David Cox's writing, there's a third type of model called an indirect model. And I won't try to summarize it here, but it's a very interesting kind of typical David Cox aside. In like 1.5 sentences, he says something that you'd never thought of before. So I encourage you to have a look. And that David Friedman wrote a book called Statistical Models. It's more like a textbook, an undergraduate textbook, but it is called Statistical Models. And I liked his comment in the preface. The emphasis in his book is on the connection or lack of connection between the models and the real phenomena. And I liked it because his whole book is kind of like what I was trying to emulate with these different examples from the scientific literature. He has 10 or 15 or 20, I forget exactly how many examples from the scientific literature, and he shows how you could do it, statistical inference, badly, or you could do it well. And being David Friedman, he doesn't pull any punches, so it's kind of a fun read as well. That's models, but models are typically parameterized, so they come as a class, and that's kind of what I spent my life's work on. The parameters might be finite dimensional. That's what I spent my life's work on, but they could be infinite dimensional. That's closer to maybe to what Grace has spent her life working on. And ideally, one or more of the parameters are going to represent key aspects of the model, and the other parameters are needed to complete the specification of the model. And of course, their meaning is going to vary with the application, but I'm kind of coming to, without saying it, parameters of interest, the key aspects, and then the completing parameters, the nuisance parameters. This sounds a lot simpler than it is. And somehow it doesn't account for the role of the data, although if we had an applied problem to tackle, we would start with the data and say what's likely to be a plausible model for this data. But in reality, I think the plausible model for the data is this is the model I'm familiar with, or this is the new model I made up that I'd like to try, one of those two. And it's to actually kind of zero in on what we're actually measuring and what we're actually thinking about, I think is quite a deep question that maybe should be studied also by the philosophers and more people in foundations. And I would recommend, although it's a hard read, I think one of the deeper approaches to this is due to Peter McCullough, who really emphasizes the role of the data in the building of a model. That is, the model and the data kind of go hand in hand. He couches it in unfamiliar language of algebra, which makes it a little bit of a hard read, but I think it's a very important paper. Okay, so now I'll get to the actual topic of my talk, which is some misspecification, and I'll describe 3 approaches, and then I'll spend some time on our recent work. So the classical approach you're probably familiar with to some extent. We have something called a true model, which we imagine exists, and we're using a fitted model that's been parameterized with parameters theta, and my boldface Y here stands for the whole data set. And we would find often the maximum likelihood estimator under the fitted model, which we get by taking the log of the density and maximizing that over theta, so that's a function of the data, of course. And if the fitted model is right, then the maximum likelihood estimator will converge to some notional true value of the parameter. But if the true model is M, not in the class that we're fitting, then theta hat will converge to kind of the closest true value it can get to, the one that minimizes the Kullback-Leibler divergence between the true model and the fitted model. Or I should say, from the true model to the fitted model. Or the other way around, I can never remember. And you can show under some regularity conditions that will have an asymptotically normal distribution. It will be centered at this closest true value, of course. And its variance needs fixing. We can't just use the fitted model to estimate the variance in the usual way. We have to use the sandwich estimator of variance, or the Gadambi information, which is comprised of the variance of the first derivative of the score and the mean of the second derivative. That part is, you don't need to remember, it's the sandwich estimator, and it's more robust than the usual estimator of variance because it doesn't assume that the model is correct. Of course, those quantities need to be estimated if we're going to use this for inference, but at least we know what we need to estimate. So I would roughly describe this as we kind of change the inference goal from some notional true model M to some parameter that's kind of related to the model that we're fitting, but not exactly. And then we just continue as usual. And you do tend to see this in much of the applied literature. You'll often see we use robust standard errors. Or the Alzheimer's twin study, they used a multi-level Cox regression with a sandwich estimator of variance because they fit random effects. So that's in the supplement, right? But it seems to be kind of like almost tossed out in many applications that, oh, just to be safe, we'll use the sandwich estimator of variance, and we're pretty sure we're estimating the right thing, but it might be a little bit off. So that's, I would call that maybe the sort of classical approach. A different approach is to make the inference function itself a bit more flexible. So to create, if you like, a misspecified model that's kind of similar to the model that you'd like to be fitting. So in this context, composite likelihood is one version of this. This was first studied in depth by Bruce Lindsay. So our true model is now for a d-dimensional observation. I still have n observations, but in d dimensions. And instead of fitting this true model, we fit something a bit simpler that just uses the density over the subsets. And one of the simplest examples is the pairwise likelihood, which just looks at the joint distribution of two components of our vector and just takes the product of all those joint distributions. So that's not the likelihood function, obviously. It's the composite likelihood function. It's not the log of the real density, but it's some kind of made-up density. In time series, you might do this by assuming for a single long observation, y1 up to yn, you might assume that you have an AR1 model when really you have maybe an AR7 or even a more complicated time series. So we're taking the successive conditional distributions and then making them all simpler by knocking off all the previous observations. And the pseudo-likelihood used in spatial data analysis, first proposed by BSAG, where you condition on the near neighbors of each point in space, is an example of composite likelihood. So in that, we change the inference function. We have now a misspecified model, and we can apply the classical treatment. For this particular misspecified model, the parameter to which the estimate converges is the true parameter, as long as that true parameter has the same interpretation in the bivariate density as it did in the original multivariate density. So that's a caveat for composite likelihood, which is sometimes overlooked. We start with a d-dimensional vector and a distribution for it, and then we say, oh, we'll just look at the joint distribution of all the pairs. Does the theta still mean the same thing? That's going to depend on the particular model details. Another more flexible one is to leave likelihood behind and go to kind of generalized estimating equations, also probably familiar to many of you, where we model just the structure of the expected value and the variance of the response, usually given some covariates, and that gives us an estimating equation. And so that estimate this is a misspecified model as well, and so we'll have the sandwich estimator variance and so on as before. An interesting variation on this that I think is less used than it should be is the quadratic inference function, where we replace the inverse variance function with a very clever expansion of the inverse covariance in basis functions and use generalized method of moments. I don't have time to talk about the details, but I think that's kind of an interesting approach to this, again, a more flexible way of conducting inference than using standard maximum likelihood. And then I feel like many people in the audience will be working in models that are just simply more flexible and wondering, well, that's obvious what you should do. Identify your parameter of interest and then use a very, very, very flexible specification for everything else. That's become extremely popular now, I think, in machine learning and in causality, but goes back, for example, to 72, to proportional hazards regression, where we have a linear regression and then we don't specify the form of the hazard or the instantaneous failure rate. Empirical likelihood, another example of this, we don't specify a particular class of models, we just identify a parameter that we're interested in, and then we let the specification be quite arbitrary after that. Another one is a sort of semi-parametric linear regression where we're interested ostensibly in a treatment effect, and instead of modeling the covariate effects as X transpose beta, we use something quite flexible. And again, even in these more flexible models, it's going to be important to know if the parameter that we think we're interested in has a stable interpretation across the misspecifications that we're contemplating being active. And that is a model assumption. And in connection with that, I'm going to spend a little bit of time just talking about the assumption lean approach of Van Steel and Dukes that was recently published with discussion in Series B. And that's why I put this particular semi-parametric regression model on the previous slide. So there's a possible model. We're interested in the treatment effect. We have a lot of covariate effects. And in particular, in this model, we're not assuming any interaction between them. So that's a specialization that could be wrong. The assumption lean approach is not to focus in on estimating beta exactly, but to define something that would be interesting to estimate whether this model works or not, whether this model is correct or not. And the particular estimand that they described, or again, I'm not doing justice to their paper, but at a high level, instead of looking at just the blue bit in the numerator, which is the treatment effect, conditional on the covariates X, they look at a weighted conditional effect, kind of weighted by the covariate propensity score, the probability of getting treatment with those covariates X. The idea being, if that model that's at the top line is correct, this will estimate beta, but if that model at the top line is not correct, it still estimates something that we would be interested in knowing about. It's the weighted average treatment effect conditional on the X's. So I've just said that it's a meaningful quantity even if there's an interaction, and it reduces to the treatment effect if the model is correct. And so this is one of many papers along similar lines that I mentioned earlier with the machine learning approach. We have some extremely flexible way to fit the kind of noise nuisance part of the model, and then a rather more specific, familiar, interpretable parameter to attack the parts that we feel that we're most interested in. And again, that's in a way similar to the simpler models that we were looking at with the first examples, but it also has maybe the same caveats, like what exactly do these parameters mean, and do we know if they have this stable interpretation over these different settings? One point to mention in connection with the Van Steelen paper is that they actually did generalized linear models, so they did everything on the scale of some known link function, but essentially the similar estimand. Okay. The discussion is well worth a read. There's many other things in the paper, how to conduct inference in this model and so on that I'm skipping, but there's a lot of discussion of modeling again, and as I was saying earlier in the talk that I felt we don't discuss this enough, and this is one place where you can go and find a lot of very interesting discussion about what models mean. And in particular, Rhiann Daniel mentioned that as your model grows more complicated, their approach doesn't allow more complicated parameters to estimate, whereas I think we would we would normally, as the model gets more complicated, feel we had to estimate, we had more parameters of interest. This one is more parsimonious than that. Didelot made the point that even if we just are using our model in the box style, all models are useful, somehow they implicitly affect the meaning of what we're doing, and we might not notice that. Several authors, including Ding, thought that that particular estimate might not be relevant for policy, and that's another whole discussion. Heather Batty's contribution noted that if the parameter of interest is to be stable, then it's possible that some version of orthogonality is needed, or at least would be useful. And the discussion by Heinz and Diaz-Ordaz discussed estimands as non-parametric projections, and in that sense, I think it connects more directly to the machine learning literature. And so that for the rest of my talk, I'm going to talk about this aspect of whether orthogonality is useful and what does it mean for the parameter to be stable over other aspects of the model. And this is based on an example. I think Heather's discussion was based on an example that appeared in Batty and Cox on exponential matched pairs, and that's why I did the survival data with Alzheimer's twins, because I was looking for plausibly exponential matched pairs. So suppose we have survival times for n matched pairs, and we randomly have assigned to each pair member to treatment or control. That wasn't the case in the Alzheimer's, of course, but it was a kind of natural experiment. The parameter of interest is the treatment effect, and the nuisance parameters are the parameters special to the pairs, which we've modeled arbitrarily with lots of, we give each pair its own parameter. This is like a name and Scott problem, right? So we have one twin has exponential failure time with rate lambda I divided by psi, the parameter of interest, and the second twin has exponential with rate lambda I times psi. We don't need to parameterize it this way, but for now we will. So psi is a common parameter of interest, and lambda are the nuisance parameters. And there's three possible approaches. We could just do the usual likelihood, maximize over all the nuisance parameters. We kind of know that's going to be wrong because we have n nuisance parameters, and as n goes to infinity, we have too many. So none of the regularity conditions hold, and that typically won't provide an adequate solution. We can find a marginal likelihood if we just take the ratio of the two responses. That doesn't have any lambda in it because of the way we've set it up, right? So that will give us information about psi squared, which gives us information about psi because it's positive. And so we could just go ahead and do that. Or we could take an approach slightly closer to a Bayesian approach and imagine a random effects model for the nuisance parameters and integrate them out. So I'll look at that random effects model. We have our exponentials, and we'll assume that the nuisance parameters now come from some distribution, conveniently here the gamma distribution. And now we have an integrated likelihood, and it's quite relatively easy to work with in this particular case. And in this model, the parameter of interest is orthogonal to the nuisance parameters. The nuisance parameters are now the parameters in the random effects distribution. And because it's orthogonal to those parameters, it converges to the correct value, and we can just work with that model. But it turned out to be the case that this psi is orthogonal to the alpha and beta, even if we had some other random effects distribution that wasn't gamma at all. It's still orthogonal to the parameters in that distribution. So this orthogonality holds regardless of the model for the random effects, and that means that the estimate from this integrated likelihood is consistent, even if the random effects model is misspecified. A caveat, it could be quite inefficient, but it is at least consistent. It could be more efficient than the nuisance parameter version where we divided out the pairs, if the model's correct, if the gamma random effects model plausibly reflects the variation among the twins, then we might prefer that. If it is just a convenient assumption that we stuck in there, then at least there's some comfort in knowing that our point estimate won't be biased in the limit at least. So the project that we worked on was to try to answer the question, can this be generalized? Because this is just one example, and that's what I'll talk about now, the formalization of what's going on in that example. So here's our try. I think it's a work in progress. This is based on a paper that will appear in PNAS shortly, I hope. I think we raised as many questions for ourselves as we answered, so that's why I'm calling it a work in progress. So we have our true model M as we had before with some notion of a true value of the parameter. So this really is like a parameter that has a stable interpretation no matter what model we're using. And it has a notional true value. And we're going to fit a model that has parameterized by the same parameter of interest and it's some collection of nuisance parameters. So as we know, the maximum likelihood estimates converge to the nearest wrong value, as I said before. But we're going to assume that we're not interested in that nearest wrong value, psi sub m sup 0. That's the limit under the classical approach, right? But we're not interested in that value. We want, for any value of lambda, we want to get back to the true value of psi in the true model. So that's the nature of the misspecification. And it's, at least as a start, this will be the case. That is, we will have convergence in probability under some smoothness conditions on the fitted model. If the expected value of the score function, so this is the partial derivative of the log of f with respect to the parameter we care about, so that's the estimating equation, if you like, for psi, except that I've put in this limit value of the MLE. If that expected value is 0, we need that expected value to be 0 in order for psi hat to converge in probability to psi. We need a bit more regularity, but we also need this estimating equation to be unbiased. But we don't know that whatever that value of lambda is, because we don't know the true model M, right? We just know, we believe it exists and it has a parameter, but we don't know what it is. So it might be easier to show that that score equation was true no matter what the value of lambda. And our first result is that those two things are equivalent if and only if the true value is orthogonal under the model, the real model, to the parameter lambda. So M orthogonal, I think the definition is on the next slide, but just linger on this slide for a minute. The thing we need is equivalent to the thing that might be easier to show if and only if we can also establish orthogonality. So the one being equivalent to 2, I've summarized it very informally as the hard part is equivalent to the easy part if and only if psi is orthogonal. And M orthogonal is like the expected value under the true model of the mixed partial derivative of the log likelihood for the fitted model is 0. If I put, instead of M here, if I put the fitted model, F theta or a theta, then that would be the ordinary Fisher information orthogonality. But this is more general. It's orthogonality under the true model. We don't know M, so it's going to be hard. But if we could establish this, and we could establish the score equation was unbiased, then we'd be fine. Okay, it's stronger than we need. It can still be consistent without this requirement, but it's at least some sufficient conditions. There's a slightly weaker requirement that's still a little bit too strong that has to do with the actual Fisher information matrix for the whole log likelihood under the model. So this may be a little bit small and faded for the people at the back, but it's the Fisher information and the score equation. Their expected values under the true model have to satisfy a certain equality. That's a little bit weaker than the result 1. So we have one result that's too strong, and we have a slightly weaker result that's still too strong. Yeah. The thing is, we can often establish parameter orthogonality in the assumed model, and that's when all the expectations of the derivatives are under the assumed model. And there's various approaches to establishing that, but that's not usually going to be the same as under the true model. There's one exception. There's a special case if we have essentially a generalized linear model or an exponential family model. If the log likelihood function is a linear in the data through the sufficient statistics. So think of an exponential family model would satisfy that. And if the sufficient statistics have the same expected value interpretation, then we can establish that the assumed model orthogonality is the same as the difficult unknown model orthogonality. This is related to earlier work by Sartori and Severini and Maris on reparameterizing generalized linear mixed models using the canonical and the expectation parameters of exponential families. It's a little bit technical, but exponential families have sufficient statistics. If we're in the canonical parameterization, it's pretty easy to get orthogonality, and this result is related to that. Okay. In the matched pairs, there's something more going on, and it has to do with the way the model's been parameterized. So when I first put it up, I said, well, we'll use this parameterization. We're assuming that in each, the treated twin that has the rate determined by psi divided by some nuisance parameter, and the untreated twin has the rate psi times the nuisance parameter. So if there was no treatment effect, then the ratio for if the psi effect was, well, the null treatment effect would be psi equals 1, and is it 1? I want to say 1, but I'm not exactly sure. No, let me say it a different way, what I said on the previous slide. If we take the ratio of the observations, then we'll focus in on the parameter of interest. So we're looking at the relative lifetimes of the two twin pairs. But in another context, we could think of adding the nuisance effect. So we could have a linear regression or a log linear regression for the expected values, psi plus lambda I and psi minus lambda I. And the calculation that Heather did won't work if we do it that way. It only works if we set it up this way. And why is that? Well, there's a sense in which the nuisance parameters enter symmetrically within this kind of exponential model, which is a scale family of models. So there's a group hiding in behind this, and it's the group that makes it work. So and when you look into the calculations, you find that you're repeatedly changing variables from y1 and y2 to the ratio and the product. So how would we generalize this? We know we want an M-orthogonal parameterization. We don't know the true model, so we can't check it. The exponential matched pairs is a scale group, and it's that parameterization that ensures the cancellation of terms. Okay. So our next result was if the joint distribution is parameterized in a certain symmetric way, which we called psi-symmetric, and this induces anti-symmetry on the score function, then we're good. So kind of a mouthful, but it's if we have a group that's parameterized in a particular way, psi-symmetric, and the likelihood function reflects that symmetry in a particular way, then we have consistent estimation under any of the models. So we can generalize that result for exponential matched pairs to other group families. So I've just said it again here, and the scale family is given here with the scale group, but it's maybe a little bit easier to look at a location family and the location group. So it's not exactly the location family that we learn in stat theory course. That would have y1 minus theta, for example. That's a simple location model on the real line. This has a nuisance parameter and an interest parameter. So the nuisance parameter, again, is lambda. And the psi functions like the group parameter, because we go from having it in the parameter space to putting it in the observation space. But the lambda just kind of hangs around. So the group action actually depends on the parameter of interest, which is a little bit different than what we see in the standard group theory. And so for the location group, we would need a model of this form. For the scale group, we would need a model of this particular form. The details aren't so important. It's more that the parameterization induces a certain orthogonality in no matter what the true model is. And if that holds, then we know we have consistent estimation. These are all the definitions. I should maybe spare you, it's still morning. But these are the sort of the particular group action definitions. Yes, let's skip that part. Okay, so high level, we have a parameter of interest that's very well defined. We have a model for nuisance parameters that might be quite badly wrong. When can we recover the true value of psi? And does parameter orthogonality play a role? And the answer seems to be yes. It might be difficult to verify directly, but at least there are some models based on groups that satisfy this orthogonality and have a particular parameter structure. There are some other models that satisfy this orthogonality as well. For example, a generalized linear model with a dispersion parameter satisfies this because the dispersion parameter is actually likelihood orthogonal to the estimating equation, so that all works. So that's another example, but it does have a particular structure. Many of the natural examples seem to involve misspecified random effects. There's a recent paper by Evans and Didelay where they use a frugal parameterization in a graphical model. And in that setting, the propensity score is kind of the nuisance function, and other aspects of the structural model in the frugal parameterization correspond to what we've called the parameter of interest. And it turns out that in their particular model, the parameters are not only orthogonal, they separate in the likelihood function. So there's a likelihood part for the psi and another likelihood part for the nuisance function. And that's what you might call likelihood orthogonal. It's not Fisher information orthogonal, which is weaker. Likelihood orthogonal is, the likelihood just factors into two pieces. So you can use the first piece for inference about psi and the second piece for inference about lambda. So it's a special case of our model, but a kind of overly simple special case. Okay, so I'll now conclude with some very tentative comments. We've only established consistency, which is not really enough, right, for practical considerations. And the asymptotic variance calculations do depend on the misspecified model, and they may be estimable, but it is more difficult to assess the efficiency of this approach. And I skipped over the approach that might be more natural. When the nuisance parameters are treated as arbitrary constants, sometimes you can get rid of them. Like in the exponential pairs, you could get rid of them by dividing. In a location model, you get rid of them by subtracting. In a rotation model, you get rid of them by conditioning on the length of the vector and just looking at the angle. So there are different ways to eliminate nuisance parameters that will be maybe less efficient when the random effects model is correct, but they'll be reliable when the random effects model is incorrect. And the one caveat, and our work doesn't apply to binary matched pairs because we're looking at groups, so we need continuous responses. But it's well known when you have binary matched pairs that you need to throw out the concordant pairs, right? So you'll often have to, in a sense, reduce your sample size from what you thought it was to the number of discordant pairs that you have in your data set. And it feels like a loss of information. And in the model where the nuisance parameters are arbitrary, there's no escaping it, but if the nuisance parameters were actually connected but through some distribution, then you would be better off to do that, and then you could use the concordant pairs to tell you about that distribution. So there's arguments, I think, in both directions for the treating the nuisance pairs as arbitrary constants or treating them as drawn from a sample. We talked a lot about orthogonality. There's the ordinary orthogonality of Fisher information orthogonality under the true model, under the assumed model. And then I talked about M orthogonality under the true model. In machine learning, the notion of Neyman orthogonality comes up a lot. And that's one version of that is to take the score function and decorrelate it from the nuisance score function by a simple regression. And that's been extended to general estimating equations, and that's used a lot in doubly debiased machine learning. So we're kind of circling around some other aspects of orthogonality that turn out to be important for misspecified or weakly specified models, but I'm not sure the links are completely clear yet. So final summary, orthogonal parameters, good. We have a slightly weaker condition than orthogonality, but still a bit strong. We have a result on exponential family models relating to that and to symmetries of parameterization. So that's kind of that's the summary of our paper. But to summarize my talk, I just wanted to point out that there's been a lot written about this over many years, and one of the privileges of having a long career is you get to see what goes around comes around. There's been a lot of discussion about, over the years, about whether or not it matters if we misspecify the random effects distribution, and I think the kind of meta result is that it doesn't matter that much. I think most of these works are focused on the more classical approach, where we decide to change the parameter we're going to focus on. So we'll just accept that the parameter we're interested in is the closest wrong parameter, whereas ours has a slightly different approach. But there is, I think, a lot of richness in the older literature, and I know that Grace would agree with me on that, because some technical reports that she wrote many, many years ago turned out to be absolutely essential for certain aspects of cross-validation and machine learning and so on. Another plug for Peter's model, just Peter's paper on statistical models says something worth another look. And finally, I'm finished, and I wanted to thank you, and I chose this picture of Grace to end my talk because I think it's a very good reminder that we should not take ourselves all that seriously. And now that my talk is over, I cannot take myself very seriously either. So thank you to Grace for all she's done, and thank you to the IMS and to you for listening. Yeah, so thank you. The question was, rather than worrying about consistent estimation under the, or for estimate under the assumed model when the true model is correct, to measure some kind of distance between the true model and the fitted model. And if, for example, the estimates of the two components of the Danby information are close to each other, then we could say that our fitted model is good enough. It's really close to the true model, so that there might be some hypothesis testing angle to assessing the difference between the true model and the fitted model. And it's a very good question. I didn't even think about hypothesis testing for this talk or study it, but yeah, there's many ways to approach model misspecification, and certainly testing whether the model fits would also be quite interesting. I do know of one example that where the ij inverse I is equal to j inverse, but I is not equal to j. So there might be some little caveats to your approach. Yeah. So the question was, what would a Bayesian think of this? And the answer is, I don't know. But more seriously, yes, there's a lot of very interesting work on Bayesian model selection, and I haven't even got close to that, but one popular approach is to put priors, of course, on a class of models and then find the best model using some posterior assessment of that. And there's probably several sessions on that. It's important work. I think Ed's maybe started it, but it's a completely different approach. We're good friends, but we totally disagree on statistics. Yeah, so the question was about the exponential match pairs example, and all I talked about was consistency, even if we got the random effects distribution wrong. But actually, if the random effects distribution is badly wrong, it can be quite inefficient. And we don't really have precise results on that. It starts to get quite difficult to work with because you don't really know anything about the true model. So we're trying to find kind of general results when you're not really sure what the true model might be. So I'm sorry, yeah, we don't have good results on inferential aspects, only consistency at this point.
And are there any known results yet?
There must be known results, but not known to me. A very important comment, and I couldn't agree more. The comment was, it doesn't make sense to talk about a model for an application without considering the application, and absolutely, if I conveyed a more abstract notion of it, it's because we got lost in the weeds, but you're quite right. I think that the notion that one of the standard models that your consultee might be familiar with is going to be fine, it maybe is more nuanced than we thought. That's my only other comment.
To what extent would you say that basically this assumption in the setup that you have a parameter you're interested in that is both in the true model and in the model you're fitting is actually a quite strong model assumption to the truth?
Yeah, good point. I don't know the answer to that. The question was this assumption that there's some true value, which I called psi star, that makes sense in the true model that we don't even know what it is. That's essential for our approach, and to what extent is that limiting the set of true models that we really are looking at? I don't know the answer to that. I don't know if it's a strong or a weak assumption. I guess I would guess that it's not that strong, given that the approach to sort of semi-parametric modeling that seems to be successful, I think we could maybe argue from that point of view that it's not so strong, but I really don't know the answer. Maybe Heather knows, but yeah.
Well, thank you so much, everyone, for your attention, and to Nancy for a truly wonderful lecture that was both foundational and also covered really new and exciting topics. And I'm so honored to present you with the
Thank you.
the Grace Wahba medal, which has a beautiful photo of Grace on it, looking extremely happy, as she always does in her photos.
Yes,
So you can add this to the collection of medals that you
Thank
have.
you very much. Thank you.
Thank you.